Okay, welcome back to week 3 of the online SAT course. Today we're going to start is the first of 4 chapters that we're going to be studying for the next 4 weeks. When we're done with those 4 chapters, we're going to get into problem solving techniques for types of problems. The first chapter is mainly an overview of prerequisite knowledge of things that are simple arithmetic or maybe basic algebra 1 topics. So if some of this is a little review to you, make sure you fast forward to what you need help with. To start, we have to right away think about what is a variable. Okay, now again, many of the times you've heard a variable, you've thought of as x, but a variable could be any symbol that takes the place of a numerical value or an unknown member of a set. So for example, if I said 2 times box plus 3 equals 9, well, I can then say to myself, okay, let me go through this problem and figure out what is this. Let me subtract 3, I'm left with 2 boxes equals 6, divide by 2, divide by 2. So box turns out to equal 3. Well, box and x are the same thing. So it's very important that we understand that when we see symbols, they can also be variables, they could be shapes, they could be an asterisk along the way, but it will be defined on the test as what it is. So again, a variable is simply something that takes the place of another value. The next thing we want to make sure we talk about are real numbers. On the actual SAT, all the numbers will be real. There will not be imaginary numbers. So for those of you that are thinking right away, okay, real versus imaginary, what is the difference there? We're not going to have imaginary numbers in the SAT exam, so you do not have to worry about that. But within the real number set, there are 2 types of numbers. There are rational numbers, and there are irrational numbers. Again, the simple definition of a rational number is something that can be written in fraction form. And many people forget that repeated decimals can all be written in fraction form. So for example, if you have a number like 0.25, well, 0.25, converting that to a fraction, we'll talk about how in a minute, but that's 1/4. That can be written in fraction form. Or if you have the value 0.3 repeating, that's really 1/3. So that's actually rational. The simplest examples of irrational numbers, are square roots of non-perfect squares. For example, the square root of 3. I don't know what that value is. It's not going to reduce to a rational number. If I was square root of 4, that's just 2. So radical 4 would turn under rational numbers because that reduces to 2. So that would be a rational number. But something like radical 3 or radical 5 or radical 4.1 or radical 3.9, any of those numbers there, those are all irrational numbers because they cannot be written in fraction form. Again, the simplest example is square roots of non-perfect squares. One question that has come up several times now on the SAT I've noticed is this. The difference between the amount of irrational and rational numbers. And if you think about it logically, there are far more irrational numbers than there are rational numbers. Because think about any value with a radical. Any value with a radical besides a perfect square will be irrational. So, 3.9 was the example from here, but what about radical 3.91 or 3.901 or 3.9001 and so forth and so on? All of these numbers will be irrational. So the irrational number set has far more numbers in it than the rational number set. Again, the rational number set has to be either, as we saw here, a terminating decimal, like 0.25, a repeating decimal, like 0.33333 forever and ever, or simply written as a fraction. Whenever we think about irrational, think about an irrational number as a radical with a non-perfect square. And if you take the square root of 3 and you take a look, you're going to see that there is no pattern to the numbers. Another very straightforward example is pi. And many people say, oh yeah, pi is 3.14. But when you look at pi, that's an approximation. Again, pi was really defined as the ratio of circumference to diameter, which turns out to be an irrational constant. And you could sit there and type in pi in your calculator and run off the numbers, and there are people that count to a million places of pi. Really does not show any intelligence there. You're just memorizing numbers, okay? And I know some people would say, yeah, there are certain extremes to that. Sure, if somebody could run off a few thousand numbers of pi, that's great. But the whole idea here that we're looking at is that pi is irrational. All right. Now, the next thing we have to look at are symbols, so comparison symbols. So if we don't understand these comparisons, it might be a little bit of a trouble for the SAT. So again, equal to, not equal to, greater than or equal to, less than, and less than or equal to. Okay, again, 5 is greater than or equal to 3, but 5 is also greater than or equal to 5, because 5 and 5 are the same number. So in that case, it can be greater than or equal to, or just greater than. But it's important to remember these, and we're going to talk about how they show up. Now, the simplest way to look at inequalities is to look at compound inequalities. We see here that we have 3 less than x less than 9. Well, how do you write that? You break it up into 3 less than x and x less than 9. But if you take a look and you look at this equation, or look at this portion, if you read it from right to left, I see this as x is greater than 3. And I see this one over here as x is less than 9. So what are the numbers that are greater than 3 and less than 9? Well, all the numbers greater than 3 look like this. It's every number to the right of 3, not including 3. Every number to the left of 9, not including 9. Well, where do they overlap? They overlap from here to here. And again, notice, you see open circles. Remember, open circles indicate it's not included in the answer. It's not included in the answer. Now, had the symbols been different, had this been less than or equal to, and this was less than or equal to, and all these over here were all less than or equal to instead of just less than, well, then we would have to color in these circles, indicating that, yes, it could also be equal to that value. So those are included in our answer. So again, closed circle, remember, a closed circle can either be indicative of less than or equal to, or greater than or equal to. Open circle is just less than or greater than. Next, on the exam, it's good to know that the test can indicate multiplication in many different ways. There are several symbols that could be used. A standard times symbol. Then you could have just the dot. You could have the asterisk. You could simply have numbers where they're with parentheses. So you could have something like 5 times 3. That's also multiplication. These are also up here again. You could have written it as 5 times 3. So let's list these in order to make it more clear. So you could have 5 times 3. You could have 5 dot 3, 5 asterisk 3, 5 3. Or in the case that you have a variable, you might just see it as like 5x. Well, there is multiplication going on here. Okay, there is multiplication. It is traditional that you do not use the times symbol like the first case because it looks like an x. Again, this looks like an x here, so you don't usually see that. These are the ones that you're going to see more often. Okay, those next 4. So, if we look at If we look at the combination of terms, we have to look at something called like terms. And many of you guys have heard this many times before. A like term simply means it has the same variable to the same power. And that's the key there. So for example, 4x plus 3y, those are different variables, so they are not like terms. 4x and 3x squared are also not like terms because of the squared. Sure, you can factor something out, we'll talk about that later, but those are not like terms. But 4x and 3x are like terms, and they become 7x. So some simple examples of this: 5xy, negative 7xy. That becomes negative 2xy. Again, because I think about the 5 minus 7, it gives me the negative 2. Same thing here, 3 and 43. So if I had 3x squared z, let's say plus 43x squared z, I have a total of 46x squared z. Again, because they are like terms, you can combine them. Some properties that are a bit of a review, but things from earlier in your career in mathematics. Addition commutative, it just means you could switch the order. Multiplication commutative, again, switch the order. Think about commutative. Think about you commuting to work. On the way to work, you commute one way, don't you? Yes. And then on the way back, you commute the other way. So if you're commuting both directions, it's like saying, okay, I can go in either direction. I can do 8 plus 2 or 2 plus 8. I could do 8 times 2 or 2 times 8. It does not matter. Next, associative. Think about associative as who do you associate with? Who are your friends at school? Well, you're in a group of friends, aren't you? So this has to do with the grouping, or who you associate with. So you notice that the grouping is 5 and 4 here. And then later on the grouping is the 4 and the 3. But either way, this still becomes 12, and this is also still 12. Same thing for multiplication. 5 times 4 is 20, and then 20 times 3 is 60. Or I could say 4 times 3 is 12, and then 12 times 5 is also 60. So again, Where are my parentheses? It doesn't matter for addition and multiplication. For division and for subtraction, it does matter later. So again, think of associative as who do you associate with. And then finally, distributive. You notice you have distributive here. For distributive, again, think of distributing. So you're literally distributing the front term, that monomial that happens to be in the front, each of the terms in the binomial. So you have a 4 times a 2x plus a 4 times a 4, which is 8x plus 16. Okay, again, you're distributing the 4 to both of these two terms. That's the first section. I know I'm going quick, but a lot of this is review. I encourage you guys, if you would like to, print out these notes ahead of time so you're not writing everything down. Okay, again, these notes are available to print, so you have them ahead of time. Next, powers. If we go into powers real quick, we think about powers as the amount of times a number is repeated, okay, when it's multiplied. So simply, the power is just the amount of terms. There are 4 of them, so this is 3 to the 4th. Again, the exponent, or the power, is the number of those numbers that occur. So if there are 4 3s, it's 3 to the 4th. If there were 5 of them, then this would have been 3 to the 5th. Again, 3 to the 5th. If there was a 6th one in here, 3 to the 6th, and so forth and so on. Now, let's continue and take a look at the meaning of exponents. So, if we look at our first example, the first example is a common mistake. A lot of people see this and they say, okay, I got 5 to the 4th minus 4 to the 5th. Well, you can't subtract those values. There's nothing you could do there. So for this kind of a problem, you need to think of this as 5, 5, 5, 5 minus 4, 4, 4, 4, and 4. Okay? Again, figure out what 5 to the 4th is, figure out what 4 to the 5th is, and simply subtract those values. There is nothing else you can do there. For the second example, though, there is a trick. What you're going to notice here is that you have a different base on each side of the equation, which gives us a little bit of trouble. Now, here's what I want you to write down. Whenever there's a variable in the exponent, so again, variable in the exponent, you need to get the same base. So what I can do is this. I can leave the left side as 2 to the 2x, and I can rewrite the right side. Instead of 4, I'll write 4 as 2 squared to the 3x plus 4. So again, I've taken this value of 4 right here and replaced it with 2 squared. This is a technique that a lot of people don't notice, and it's very simple. Because now, you'll notice that you have a power raised to another power. When you raise a power to a power, you have to multiply those powers. So this equation simplifies to be 2 to the 2x, again, equals 2. Now this is going to be, I have to multiply this 2 to both terms. I'm distributing it. So this will become 6x plus 6. Now you have an equation with the same base. So simply take your exponents, 2x and 6x plus 6, set them equal, and solve. Subtract the 6x, you're going to get negative 4x equals 6. So x equals 6 over negative 4, or simply negative 1.5. Okay? Good luck guessing on that one, though. Again, it's very difficult to go through these problems and just try values for x. It's very important that you understand that there are simple ways to do it if you just change the base so that you have the same base. Again, the goal was to get this 2 on each side. And then from that point, we realized we had a power to a power. We had to multiply those powers. Let's continue on down. So, for laws of exponents, if you want to multiply powers, you have to, okay, you have to have the same base. That's the whole key. If they don't have the same base, you can't do it. And the simple way to think about it is this. This is really 2, 2, 2, 2. That's those 4. That's 2 to the 4th. Then I've got 2 to the 3rd, which is really 2, 2, 2. Well, how many 2's do I have total? I could see 4 and 3, that's 7. So this is really 2 to the 7th. So what's my derivation, or what's my rule? My rule is simply take each exponent and add them to each other. So again, when you multiply two things with the same base, multiply these two numbers here, it's simply c to the 5 plus 9, or c to the 14. So it's very important that you remember, x squared times x. This is x to the 3rd, because there's really a 1 here. And you're adding the 2 and the 1 to give you this 3. Again, different bases you cannot do. Again, different bases you cannot add, you cannot multiply. You need to have the same bases. To divide powers, it's the exact same rule, except you subtract. You subtract. Okay? So again here, 3 to the 6th and 3 to the 2nd is really like saying you have 6 of them up top and 2 down below. These 2 cancel with these 2. You're left with 4 3s there. Well, there's your 3 to the 4th right there. Okay? Again, they only cancel, these 3s. These 3s here only cancel because everything is factors. Again, these are all factors. There's no add-ins. Nothing's being added or subtracted. Same rule applies. If you don't have the same base, you cannot divide. Now, one thing that is good to notice is this. What if you had a bigger number on the bottom than the top? So say you had x to the 3rd over x to the 7th. Okay, well, you got to subtract. Well, 3 minus 7 is negative 4. So yes, this is x to the negative 4. But as you know, a negative exponent means make it positive and move it down to the bottom. So this is what's really going on here. So again, you could think of this as these 3 cancel with 3 of these, leaving 4 behind. Okay? So the numerator is done with. You're left with the 1 here, and the denominator you're left with x to the 4th. Either way to think about it is perfectly fine. Let's take a look at the next example. All right. If 3 to the k equals 4, what is the value of 3 to the 2k? Well, there are many ways to do this. You can try and solve. Good luck with that. It's going to be very confusing to solve for k here. You're going to have to go back to logarithms. Now, it's a much easier way to do this. Again, it told you that 3 to the k was equal to 4. How can I get 3 to the 2k? Well, I could say to myself, I could take this side and square it, because again, if I square this side, I have k and I have a 2, and when I raise a power to a power, I have to multiply those powers as seen here. But if I square the left side, I have to square the right side. So 3 to the 2k is really 4 squared. Well, 4 squared is just 16. So this problem is a tricky one because several things. It says, what is the value of 3 to the 2k? It does not ask you for the value of k. So please don't try and solve for k here. Go right to 3 to the 2k. Once you know the value of 3 to the 2k is 16, you're done. You never have to solve for k in this entire problem. I encourage you not to solve for k here because, again, you would have to use logarithms and it would get a little messy. Let's continue. Order of operations, by now I hope everybody knows, but again, make sure you lump these together. Okay? Parentheses, then exponents, then multiplication, division, and then addition, subtraction. Again, it depends on which one comes first to left. Okay? For left to right, first or second. So I see here that parentheses comes first, so I'm going to result this to be 5 plus 18 divided by 3 squared times 6. Exponent is next, so still 5 plus 18 divided by 9 times 6. Next is going to be multiplication and division. Well, division comes first. I'll do 5 plus, now this is 18 divided by 9, which is 2, times 6. Next comes multiplication. I'm going to see the 2 times 6 is 12, so this becomes 5 plus 12, which is simply 17. Okay, PEMDAS is very important. When in doubt, use your calculator at least. Okay, make sure you have all your parentheses in there correctly. Square root and cube roots of radicals. Okay, there are many, many properties and rules that you need to remember for square roots and cube roots and such. The easiest way to think about these properties is to think about variables, and I'll explain that in a minute, but keep that in mind. Now, this thing is called the radical. Okay, the radical. The radicand is the number underneath it. The radicand, okay? So for example here, 45 is the radicand. Okay, 45 is the radicand. Next, if you have something where you have a little number in front of the radical like that, it's called an index, okay? And what that means is a cube root. So in that case, you need to find a number 3 times that multiplies to give you those numbers. So for example, here's your perfect squares. This is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6, 7, 8, 9, and 10 squared. Well, what are your perfect cubes? Let's take a look. Let's just go up to 6 for now. So let's say 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 is 125, 6 is going to give us 216. Now, how did I get those, you might say? Okay, well, this one is just 1 by 1 by 1. Okay, this one is 2 by 2 by 2. This one is 3 by 3 by 3. Again, there are 3 of them. So these are your perfect cubes that might be good to know. Now, before we break up perfect squares and perfect cubes and talk about rationalizing and all that fun stuff, let's go into our rules first. So, taking a look at our rules. Take a look at our rules here. The first rule is the multiplication rule. Again, if you're multiplying two things, you can only multiply what's on the inside and what's on the inside and what's on the outside with what's on the outside. So for example here, for this one, it's very simple. 5 by 9 is 45. Good. Let's look at a more complicated one. 2 root 3 times 3 root 7, or let's say 4 root 7 in this case, just so we don't have any misconstructions with the 3's. If I were to multiply these, I multiply the outsides. 2 times 4 gives me the 8. And then I go ahead and I multiply the insides. It's going to give me radical 21. So again, think of them like variables. If these were variables and you had 2x squared times 3x to the 4th, you multiply the outsides, that gives you the 6. And then x squared times x to the 4th is x to the 6th. So it's the same rules as if you had variables. Outsides, outsides, insides, insides. Now, the next part, the same exact rule applies. If you're dividing, you divide the outsides with the outsides and the insides with the insides. The third property is one that everybody should know by now. If you take a square root and you want to get rid of it, you must square. Excuse me. If you notice here, you're going to see, okay, square root of 6 squared, sure, that makes sense. This is square root of 6 times square root of 6, which is square root of 36. Well, that comes back down to the 6. So again, the radical and a square on the outside drop off. And whatever this number was in the middle will be your answer. That's how you solve a square root equation. You always take the square of both sides. Number 4 just indicates to us that you have to follow the same rules as variables again. You cannot add or subtract unless you have a common radicand. So for this example, I want you to think of if you have 2x plus 3x. Yeah, sure, that's 5x. What did you do? You added the front numbers, and then you repeated whatever the variable was. That just repeated itself over here. Same thing goes again. Add the 2 and the 6, you get the 8, and repeat the 5. Okay, repeat the 5. So whenever you're adding and subtracting radicals, your radicand must be the same. Your radicand, the 5, must be the same. Okay, again, this is not negative ones. That's underlining, that's an arrow. These are arrows pointing to each one of these. Number 5 is very important to notice, and a lot of people mess this up in the simple example here. Okay, the very simple example given here. So if you wanted to know what the square root of 4 plus 9 is, you cannot break it up into components. Okay, you cannot do this. This does not work. Try it. Square root of 4 plus 9 is really saying, okay, that's the square root of 13. Well, if you do it this way, you end up getting 2 plus 3, which is 5. Is the square root of 13 the same thing as 5? Absolutely not. Again, absolutely not. So you cannot break up. You cannot break up two addends that are underneath the radical. Okay, again, you cannot break that up. You can break it up, though, if you have multiplication or division. Keep that in mind. Okay, whenever you have multiplication or division. So if you ever had something like this, radical 3 over 25, you can make this root 3 over root 25, which in turn just becomes root 3 over 5. Okay, again, a radical and above a quotient or around a quotient can be broken into those terms. Same thing goes for multiplication. Okay, if you have radical 6 times, let's say, 9, sure, I can make it root 54 and then figure out how to simplify it, or I could just make it root 6 times root 9, but root 9 is really 3, so this becomes 3 root 6. Okay? Again, the 6 carries down, sorry, the 3 goes straight down there. Good to know. Now, to simplify a square root, we're going to use what we just showed right there. The whole idea is to find two numbers that multiply, one of which is a perfect square. So the example is quite simple here. Radical 72. Well, radical 72 can be broken up into 9 and 8. Can be broken up into 18 and 4, 36 and 2, 12 and 6, and 1 and 72. Look at all those combination of factors. Now, here's what you want to notice. You want one of them to be a perfect square. Well, here's the problem. There's a perfect square here, there's a perfect square here, and there's a perfect square here. There's not here and there's not here, so those are out for sure. But again, 36, the 4, the 9, those are all perfect squares. Which is the biggest? Well, yes, your answer is 36. You choose the largest. Square root of 36 times 2 is broken up. Make the root 36 a 6. Carry over the 2. So your answer is 6 root 2. Okay? The final thing to look at, Okay, and this is rationalization, and you will only have to rationalize a simple denominator, not a binomial one. We'll talk about that later in the year. But for the SAT, you do not need to use a binomial denominator. The easiest way to get rid of a radical in the bottom or in the denominator is simply to multiply by that radical over itself. So in this example, this is the answer that we got. Well, you can't leave a radical in the denominator, so you take that answer, multiply by the radical over itself. Radical 3 and radical 3 in the denominator here becomes radical 9. 5 times radical 3 in the numerator just remains 5 radical 3. But radical 9 turns out to be 3. So our answer, okay, has no radical in the denominator. Okay, no radical in the denominator. That's the key we want to notice there. No radical in the denominator anymore. Okay, try other examples on your own for that one. Put like something like a radical 7 in the denominator. See how you do for that one. Next, divisibility and factors. So we have to start by looking at long division. We have to figure out for each one of these values if we can see if each one of them actually goes into this number wholly. Sorry about the interruption there. Okay. So again, we're trying to figure out, does this number divide into the dividend wholly? So for example, if we start with a simple example, what is 7 divided by 3? Okay, so we look at long division. 7 divides by 3 twice, that's the 2. 2 times 3 is 6. 7 minus 6 is 1. So our answer here is really 2, remainder 1. Well, if you take a look at the number 7 divided by 3, really, you could also say 7/3 like this. And you could say, well, that converts into a fraction. This goes in 2 times with a 1/3 remainder. Well, where do these numbers come from? The quotient, okay, your answer comes over here. The number that you're dividing by, or your divisor, which happens to be a 3 in this case, the divisor, 3, becomes the denominator of the mixed fraction. The remainder becomes the numerator. Okay, so again, whenever you divide two values, think about the fact that your final answer is always going to be the quotient plus the remainder over divisor. This should be familiar. We did this with synthetic division. And if you have me for class, you're going to remember this from concept 33. Concept 33 was synthetic division, where we had a whole polynomial function, and then we had some remainder over the divisor, whatever the divisor happened to be for that long division problem. Okay? It's good to know that when the remainder is 0, it means that it is divisible. So for example, 8 divided by 2, yes, that's just 4. What's the remainder? It's really remainder 0. But we don't write that because 8 is divisible by 2, and its result is 4. Okay? The next thing I'm going to go through pretty quickly, but it's important that you understand how much this could be used on the test. Odd and even numbers. I know it sounds very simple, but the rules need to be down pat. Because a lot of these problems give the examples of SAT problems where it's like 1, 2, 3. They give you 3 conditions, and the multiple choice says, which of the following 3 statements is always true? And then your 5 choices are like 1, 2, 3, 1 and 2, 1, 2, and 3 maybe. Okay, those would be like choice A, B, C, D, and E. Okay? So again, the idea is that you have to know the rules. An even plus an even is always going to be even. If you add an odd and an odd, you're still going to get an even. Okay, if you add an odd and an odd, you're still going to get even. But if you add an odd and an even, you get an odd. If you multiply an even times even, you still get an even. If you multiply an even times an odd, though, you still get an even. That's where it gets a little bit tricky here. Okay, again, notice these two are switched for these two answers. Okay, when you multiply an odd times an odd, 7 times 5 is 35. Same thing goes for positive and negative, okay? And we're going to talk more about positive and negative at some point. Let's go to factors and multiples, okay? Again, most people forget these terms. They forget them. A factor is something that divides into a value. So for example, 32. 32 could be broken into 1 and 32, 2 times 16, or 4 times 8. So those are all the factors of 32. Whereas the multiples of 32, are simply multiplying times 1, multiplying times 2, multiplying times 3, multiplying times 4, etc. So we take 32, we double it, we triple it, quadruple it, quintuple it, and so forth and so on. These are your multiples. Again, know the difference, please. The most important thing for multiples is when you're looking at your least common multiple or your least common denominator. So for example, if you had a number like 3 and another number, let's say, let's make this an easy one, actually. Let's start with an easier one. What if we had something like 2 and 4? Well, the multiples of 4, okay, the multiples of 4 are simply 4, 8, 12, 16, and so forth. The multiples of 2 are 2, 4, 6, 8, 10. And we're going to notice that there are some that are common. There's a common, there's another common, there'll be a bunch more. But what is the least common multiple? It turns out to be one of those two numbers, actually. Okay, and most people forget about that. Now, if we though then take a look at this, something like, what are the common multiples of 3 and 7? Well, the multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, dot, dot, dot. Whereas 7 is 7, 14, 21, 28. So right away, you're going to notice that the least common multiple of these two happens to be the product of those two numbers. Again, 21 is really the product of 3 times 7. So the least common multiple of 3 and 7 happens to be the product. That's always your safe bet. But for the 2 and 4, the least common multiple happens to be one of those numbers itself. It is good to know about factorization. We're going to talk about that in a sec. Before we get there, let's talk about the difference between prime and composite numbers. One of those questions in the test that comes up all the time. A prime number, again, can only be divided by 1 and itself. Okay? A prime number has factors of only 1 and itself. That's the key point there. Prime numbers start at 2. 1 is neither prime nor composite. Okay, keep that in mind, and we'll talk about that too. It's written right here, but keep that in mind. 1 is an exception. The only factors of all these numbers are 1 and itself. 1 and 2, this is 1 and 3, this is 1 and 5, this is 1 and 7, this is 1 and 11, and so forth and so on. A composite number, first of all, has more than just the number in itself. So any even is a composite automatically. Again, any even. Now, sorry, I apologize. Not 2. Not 2. Let's see. Okay, good. Prime factorization. The easiest way to think about prime factorization is the factor, factor, factor. Don't stop factoring. So 18 is an easy example, because 18 is really 9 times 2, but 9 is really 3 times 3 times 2, and now you're done, because those are all primes. But if we start with one like 36, let's say we decided to choose 12 times 3. Sure, that's right, but this is really 4 times 3. But this is really 2 times 2. So as you can see, 12 is really 4 and 3. 4 is really 2 and 2. So the prime factorization of this number becomes 2 squared times 3 squared. Again, how do I know that? There's 2 2's and there's 2 3's. This one could be written as 3 squared times 2 also. Okay, that's what our prime factorization is. It means that all of the factors are prime numbers. Until you keep breaking it down, you do not stop. So let's do a more difficult example, one that's a little bit higher than that. Let's say we had a number like, oh gosh, 128. All right, well, right away I see that, okay, that's 2 times 64, awesome. But then 64, that really, oh no, 2 times 64, 64. I happen to forget. Well, let's say I thought it was 8 times 8. Great, that's good. That works, 64. But 8 is really 4 times 2. Awesome, but 4 is really 2 times 2. So what do we end up having here? How many 7s? We have how many 2's? We have 7 of them. So the prime factorization of 128 happens to be just 2 to the 7th. It's one of our powers of 2. We're going to pause here for part 1 of week 3 video. This is week 3 video, part 1. Part 2 will be a separate video file to watch. So look for this week 3 part B in a little while.